Hi guys, so this is going to be a video on calculating the rate law. So the rate law of a chemical reaction describes the kinetics of the reaction, right? It describes how the reaction rate will change as you change around the concentrations of your reactants, right? So in this case, for this particular reaction, we have A plus B yielding 2C, right? And so the rate law will always take the form of R is equal to K, which is some proportionality constant, times the concentration of the first reactant to some power, times the concentration of the second reactant to some power. Okay, so it's impossible to know beforehand what the powers of these reactants are going to be, so we have to run experiments in order to try and figure it out. And so down below we have some example data that will allow us to do just that. For trial 1, we have A at 0.50 molar, B at 0.50 molar, and so the rate at which you measure this, right? Rate can be measured in all sorts of different ways, but for this experiment, you might choose molar per hour. So the rate here is 1.0. For trial 2, A has a concentration of 1.00 molar, B has a 0.50 molar, and the rate is 4.0. For number 3, A is 0.50 molar, B is 1.00 molar, and the rate is 2.2. Now, if you notice, the concentrations for each of these trials is a little different, and that is on purpose, right? Because if we vary the concentration, we'll actually be able to get the powers of the rate law, okay? And so let's do that. In order to figure out what those individual powers are, we need to consider reactions that only change one chemical at a time. The reason for that is because if you consider the ratio between, let's say, two reactions, well, we don't know what the value of K is to start with, the proportionality constant. So by taking this ratio, what happens is that the proportionality constants actually cancel out. And so what we're left with are just the concentrations of each of the reactants, right? So we have A, 1 to the A power, times B, 1 to the B power, and then divided by A, 2 to the A power times B 2 to the B power. Okay, the rate law for every single trial is always going to be the same, assuming the same reaction conditions. And so we can always write a rate law for each trial. The concentrations of trial 1 up top, concentrations of trial 2 on the bottom. The reason why we have to keep the one of the chemicals the same, or all of the chemicals is the same except for one that changes, is because then it allows us to make some assumptions and just cancel out the ones that remain constant. Okay? So how do we choose these? Well, if we compare these trials, we'll be able to see which ones are changing. If we compare 1 versus 2, trial 1 versus 2, we see that the concentration of A is actually doubling. Okay, so the concentration of A goes from 0.50 molar to 1.00 molar, and that is the only change in that reaction. With this doubling of the reaction rate, we get doubling of the concentration, we get 4 times the rate, 1.0 to 4.0. If we compare trials 1 versus 3, we see that the concentration of B has changed. It went from 0.50 molar to 1.00 molar. Again, with a doubling, right, this time the reaction rate has also doubled. Okay, and that's just quickly looking at, okay, the rate went from 1 to 4, so I know it times by 4, and then the rate went from 1 to 2.2, so it's roughly 2 times. To go through the more formal calculations, what you do is you write the individual rate laws for each trial. Okay, so let's say we're looking at reactions 1 versus reaction 2. Well, that means that the rate law for trial 1 is going to be K times the concentration of A to the A power for trial 1 times the concentration of B to the B power for trial 1. Okay? And so the concentration of A in trial 1, if we look back, was 0.50 molar. When we take a look at the concentration of B for trial 1, that was also 0.50 molar. Okay? We can do the same thing for rate 2. That is equal to K times concentration of A for trial 2 to the A power times the concentration of B for trial 2 to the B power. If we took a look at the concentrations for A2 and B2, looking back, A was 1.0, B was 0.50 molar. Okay, so again, we can take a ratio in order to cancel out a lot of these terms. Okay, the rate for reaction 1 was equal to 1.0. The rate for reaction 2 was equal to 4.0. Okay. So, again, let's substitute a lot of these things in. Okay. Proportionality constant cancels, right? So what we're left with is 1.0 divided by 4.0 is equal to, okay, so the concentration of A is changing, so we have 0.50 divided by 1.00 to the A power. Okay, what I'm doing is I'm using the rule where if numerator and denominator are raised to the same power, the whole fraction is raised to the same power. Okay, B, notice B doesn't change, right? B1 and B2 are both the same, so we can actually cancel that out. Okay, and what we're left with is this expression, in which the only variable is A. So now we have to solve for it. What we'll get when we do some quick calculations is that we'll get 0.25 is equal to 0.50 to the A power. Okay, that is 1/4 is equal to 1/2 to the A power. Okay, well, if we actually substitute A is equal to 2 into this equation, it will make sense. So A will equal 2. I did that by converting to a fraction and then just knowing that if I multiply a half by a half, I'll get 1/4. But if you really didn't know what to do, well, what you can actually do is take a logarithm of both sides. And so I'm going to delete all of this, and I'm just going to go through the logarithmic way. Okay, so what we do is we take a natural log of both sides. So ln of 0.25 is equal to the ln of 0.50 to the A power. Okay. Now, one property of logarithms that makes this useful is that it can turn powers into multiplication. So we can actually bring the power of A down to the front. So we have ln of 0.25 is equal to A times the ln of 0.50. Okay, so now it's pretty easy to just solve for A. We just divide both sides by the natural log of 0.50. So we have natural log of 0.25 divided by natural log of 0.50. If we plug that into a calculator, and let me just bring up a calculator real quick, the ln of 0.25 is equal to negative 1.386. The natural log of 0.5 is equal to negative 0.693. And so if we take those numbers, negative 1.386 divided by 0.693, we do indeed get 2. Okay? And so now we know that in the original rate law, A is equal to 2. We can do the same thing for B, right? And I'll leave it to you, but if we do the calculation for B, it will be equal to 1. Okay? Oftentimes, this number isn't going to be perfect, so what's recommended is that you round to the nearest quarter. Okay, there can be fractional powers, that is allowed. Generally, they are whole numbers, but there can be fractional powers. Okay, hopefully that helps. Take care, everyone.